Good afternoon, ladies and gentlemen, boys and girls, friends and neighbors. Uncle Lee back at you here with a little story about Optimization 101. Optimization in pre-calculus. Optimization problems are pretty prevalent in calculus. But before we get there, we have to do some modeling in pre-calculus. This is going to be an easy problem once we get to where we want to go using our graphing calculator. So what do I mean by optimization? It's an optimization problem. What an optimization problem does is it's going to find a maximum or a minimum. We're going to maximize or minimize a particular function. I.e., what we want to find out is where does the absolute max or absolute min happen for that particular function. Most of the time they ask you, hey, where does that absolute max in? In this particular function, this is what we're going to use our modeling skills to develop. And this is the practicality of this particular type of problem comes into play. So, example number 1. What we want to do is consider a rectangle inscribed in a semicircle of radius 2. So we're going to inscribe a rectangle within a semicircle of radius 2. And the equation of the semicircle is going to be y is equal to the square root of 4 minus x squared. What do we want to do? We want to find the x value that yields the maximum area, the area of the rectangle, the largest rectangle that I can inscribe in this semicircle. That's what we want to find. And then we might, as a little addendum, find what the maximum area is for that rectangle. So let's look at this. Let's start off by just looking at this semicircle and see what we're talking about here. This is the semicircle. This is the equation of the semicircle. Y is equal to the square root of 4 minus x squared. Nice, nice. And what we're going to do is we're going to inscribe a rectangle in there. Let's take note of some important points on this semicircle, if we can. This point right here, 2, 0. This point right here, negative 2, 0. And this point here, 0, 2. So this is my semicircle. What do I want to do? I want to inscribe a rectangle within that semicircle. Okay, so that's just that's a picture of one of many rectangles. Okay, that may be the one with the maximum area, it may not. What we're going to do is we're going to find this x value right there that yields the maximum area of that rectangle. What's a good idea to do is look at some other rectangles that could be inscribed and start comparing. Hey, what about another rectangle? Here's another way you can do that. So let's look at that rectangle. Now there's a rectangle inscribed. What rectangle has the larger area? What rectangle has more area? This rectangle or this rectangle? It's really hard to say. It certainly looks like the red rectangle, doesn't it? Let's inscribe another one and let's just see here. Can we do a rectangle in let's do a rectangle in blue. Look at this rectangle. Let's go. Hey, what about this rectangle right there? But this is just going to give us an idea. Ooh, now it's really hard to say. Is the orange one larger than the red one? I don't know. But we can find this very easily with some appropriate mathematics. So what do we want to do? So here's that rectangle, and here's x sub 1. What I want to do is to maximize the area of this rectangle. Well, the area of any rectangle is base times height. Please do not make this problem more difficult. This is Optimization 101. This is not Optimization 303 or 427 or 464 or Optimization 101. This is what I want to optimize, the area of that rectangle. The area of any rectangle is base times height. This is the base of that rectangle, and this is the height of that rectangle. So what I need to do is I need to put b and h in terms of x. Well, if I look at this guy right here, this semicircle is symmetric about the y-axis. So if this is a particular x sub 1, and I'm only looking at half of it, this distance right there is the same as this distance, because the rectangle is inscribed. So this distance is the same as this distance. And keep in mind, we're only dealing with distance here. If that's the case, what's going to be the value of the base here? And this is an arbitrary x value. We're going to call it right now x sub 1. We're going to eventually just call it x. And that's okay. So, if this guy is x and these guys are the same distance, what's the base? Yes, you are correct. The base is, ladies and gentlemen, oh, forgot to put on my pen. The base is 2x. So all I need to do now is find h in terms of x. H in terms of x. H in terms of x. So here's my 2x. Well, look at this. What is it? Oh, look. Is it the h? The h is the y value associated with that x. I've got a y value associated with that x. And I could go back to this other convoluted picture that I have here. And you would see it. So if I would have this x, this would be my y. This would be my height. And if I use this, this would be my height. If I use this x, this is my height. This y. This y or this y. So the height in either way, the height is always going to be whatever the y value is. It's that easy for this particular problem. So that's why, for this particular problem, the h is just the equation in x of y. Y is the square root of 4 minus x squared. So therefore, my area is 2x times the square root of 4 minus x squared. Now next year, what we're going to just slow your roll. Next year, what we're going to do is we're going to use calculus to analytically find where this maximum area happens at. And we're going to discuss why this area indeed has a maximum. Right now, at this point, we're just going to use our graphing calculator. We're going to be, whoo, good deal that we found the area. But what we're going to do is we're just going to put this rascal right there in my graphing calculator. And we're going to find the x that yields the maximum area. Sounds easy enough. Sounds easy enough, correct? Well, maybe not. What do we have to do first? Before we do that, one thing we have to do is we have got to find, ladies and gentlemen, boys and girls, we have got to find the domain of A of x. We have to find the domain of this area. And this is important for these problems and important for these optimization problems. Important for any practical application of mathematics outside the mathematics room. You have to realize what the domain is of the relation that you're talking about, the domain of the function that you're talking about. And this domain is fairly straightforward. If I go back to my previous graph of that, I can actually visually look at that domain pretty darn easy. Well, it's clear that my x can't be greater than 2. If my x is greater than 2, my rectangle is no longer inscribed in the semicircle. But what about the least value? So x has got to be less than 2 because of that point. If x was equal to 2, could x be equal to 2? Well, if x was equal to 2, the height of the rectangle would be 0. I would have no rectangle. All I would have is a line. But what about, what's the least value of x? A lot of people want to think, well, hey, x can be, the domain is from -2 to 2. That's the domain. No, it's not. And why isn't it? It isn't because we're talking about the area. And whenever we're talking about area, base and heights have to be positive. So if I look down here and if I look at my area function right here, that is 2x represents the base, x can't be negative because as soon as x is negative, I have a negative base. Negative bases cannot happen in geometry. Bases have to be positive. So x has got to be greater than 0, nor can x be equal to 0. If x is equal to 0, my base is nothing, and my height is 2. Again, I just have a line segment and not a rectangle. Therefore, the base has to be, ladies and gentlemen, boys and girls, not the base, sorry, the domain of my function has to be greater than 0, less than 2. And now let's see, let's take my graphing calculator and let's see if indeed I have a maximum area. I may not. So I'm going to pull my graphing calculator, my old school graphing calculator over here, which I hate to use, but my software is currently non-functional. Well, this is going to be nice, probably in the way of video. So let's go down here. I think I can do it right here and still be caught in the video. Still catch everything that's going on. So look here. I'm going to put my function in. There's my function. 2x times the square root of 4 minus x squared. I'm going to go up to my window. I'm going to make sure I have appropriate. I'm just going to go from negative 0.5 to 2.5. So therefore I have my 0 to 2. I like to see my y-axis. I want to get a little bit farther than the maximum value of my domain, which is 2. And then my area should be always positive, so I want to see my x-axis. So I'm going to let my y-min be negative 1. And I'm just going to try y-max of 10 and see if I can get a graph of the area. Oh, and there it is. And there is the graph of that area function. See if I can straighten it out there a little bit. Oh, and where it is, I can visually see now where that maximum happens at. It happens right here. There's the maximum area. So what I want to do with my calculator is I want to find out where that maximum happens. And we know how to do that. I'm going to come over here and grab my graphing calculator. Easy enough. I'm going to go second calculate 4 for max. Get to the left of that rascal. Get to the right of that rascal. Push enter 2 times. So my maximum looks like my maximum area happens at 1.41423132. We're going to round it to 3 decimal places. So my maximum area is going to happen at 1.414. And and right away, this is going to be my maximum area that happens at 1.414. So let's turn this off. I think I have this written down here. I'm going to make sure that I do before I go to my next slide. And I do. I think I do. Do I? I don't. So the maximum area happens when x is 1.414, and the maximum area is A of 1.414, which was equal to 4. So this, ladies and gentlemen, was a very simple Optimization 101 problem. What we will do next year is we will use analytical methods, derivatives, to find where that area has a maximum at. So thank you very much. Good luck with your optimizations.